9.7.1 Probability. The objective is find the probability of an event using theoretical, experimental, and simulation methods. The key vocabulary is probability, the measure of how likely an event will occur. The probability of an impossible event is 0, means 0% chance. And the probability of a certain event is 1. So if something is 100% chance going to happen, then the probability would be 100% expressed as a regular number rather than as a percentage, which would be 1. Sample space is the set of all possible outcomes to an experiment or an activity. Sample space. 3 coins are flipped and the results are recorded. So in each coin, we could get heads or tails. So we could get heads, heads, heads. We could get heads, heads, tails. We could get heads, tails, heads. Or heads, tails, tails. So I think that's all the ways that you could roll heads first. Or flip and get heads first. If we got tails on the first coin, then we could get heads, tails, heads, heads. We could get tails, heads, tails. We could get tails, tails, heads, or we could get tails, tails, tails. The key thing about this is that we have 3 coins and each of them have 2 possible outcomes. So if coin 1 has 2 possible outcomes, coin 2 has 2 possible outcomes, and coin 3 has 2 possible outcomes, there should be 8 items in my sample space, which is what I have. A bag contains 2 red chips, 2 blue chips, and 1 green chip. 2 chips are removed. Order doesn't matter. So if order doesn't matter, then that means red-green is the same thing as green-red. In our previous example, we treated tails, heads, heads differently than heads, heads, tails because order mattered. In this case, order does not matter, and therefore we are not going to list those things twice. So we could get red, red. We could get red, blue, and we could get red, green. We could also get blue, blue, and we can get blue, green. Experimental probability. This is when you use data gathered from observation. So anytime you hear someone's batting average or their free throw percentage, it is based on previous hits at bat, shots at the line, whatever it happens to be. So it's an observable thing of successes over the number of times it was tried. A softball player got a hit in 20 of her last 50 times at bat. What is the probability that she will get a hit in her next at bat? So the probability of a hit would be equal to the number of hits we've seen that softball player get over the number of times they've been at bat. So 20 over 50 or 2/5. Theoretical probability is something like a die. So we already know for a standard die that all 6 sides have an equal probability of coming up. So we don't have to run experiments on that to happen. So in this case, if an event E has n equally likely events, has a number of equally likely events, that's what NE means, is how many events are possible. And its sample space, N of S, which is the size of the sample space, the probability of event is the following. So the probability of the event is equal to the number of ways to be successful that's what your N of E is equal to over number of ways for something to happen. So that's going to be your entire sample space. So for example, getting a 5 on one roll of a standard number cube. There's 1 5 out of 6. So the probability of 5 is 1/6. Getting a sum of 5 on one roll of 2 standard number cubes. So we're going to treat this like we're rolling them both at the same time. And that 2 plus 3 is not different than 3 plus 2. So 1 plus 1 doesn't do it, 1 plus 2 doesn't do it. You could actually make an exhaustive list. And actually that may be the best thing for us to do to figure out how many possibilities there are. So let's see. We could have a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, and a 1 and a 6. And if we're not going to say that order matters, then we'll start with 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, because we don't need to write 2, 1 since 12 is already there. Then 3, 3, 3, 4, 3, 5, 3, 6, and then 4, 4, 4, 5, 4, 6, 5, 5, 5, 6, and then 6, 6. So this will tell us the size of our sample space. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So probability of a sum of 5 is going to be over 21 because those are the combinations that we have if we treat it like order doesn't matter. A 1 and a 4 will give us a sum of 5, and a 2 and a 3. So there are 2 ways out of the 21. Being dealt 2 consecutive face cards from a standard deck. So that's going to be the probability of a face card on the first draw times the probability of a face card on the second draw will equal the probability of 2 face cards. So what is the probability of a face card on the first draw? Well, there are 52 cards. There's a jack, queen, and king in each suit, and there are 4 suits, so the 12 of them are face cards. So that would be your probability, 12 out of 52 for the first card. On the second card, well, there's no longer 52 cards left. There are 51. And if you got a face card on the first draw, then there are only 11 of those left. And so we have to multiply the probability of getting a face card on the first draw, not replacing it, by the probability of getting a face card in the second draw, which gives us 132 over 2,652. If both things have to happen, then you multiply. A batter's strike zone is 17 by 22 inches, and a high inside strike is 4 by 6. So this is 17 by 22, and we've got a high inside strike zone of 4 by 6. What is the probability that a pitch thrown at random in the strike zone? So they're already telling us that it's in the strike zone. So my sample space is going to be the area of this whole strike zone. And then the successful part is the area of the high inside strike zone. So in this case, 4 times 6 over 17 times 22, which is going to give us 24 over 374 as the probability that a pitch thrown in the strike zone will also be in the high inside strike zone. Simulations, sometimes actual trials are difficult to conduct. In these situations, you can estimate the experimental probability of an event by using a simulation.